Assalamu alaikum. This is lecture number 41 of Advanced Cost and Management Accounting. We are going to consider the topic of linear programming today. Linear programming. Linear is a word that comes from the word line. So we are going to look at a program which involves drawing lines on a graph. So linear programming is a mathematical tool that is used for solving problems of scarce resources. We have earlier discussed scarce resources, and we adopted the means that if you have a scarce resource, whether it is labor or whether it is material, then the contribution per the scarce resource is calculated. So you find out what is the contribution per unit of scarce resource. If we are looking at labor, we will then see what is the contribution obtained from 1 hour of labor. If 1 unit of labor is 1 hour, we will see what is the contribution obtained by the manufacturing company with 1 hour of labor. So we take the total contribution, you divide that by the labor hours, and you get contribution per hour. And then the way to proceed was to maximize the profits. We try to maximize the contribution from the labor hours. So if you have more than one product to produce, then we will take the contribution from labor hour for each product, compare the contribution per labor hour, and whichever product gives us the highest contribution per labor hour, that is the product that we will produce first, and the other products are going to follow. So that's the basis of maximizing profits from use of scarce resources. Let us just think and try to understand this scarcity of resources. What are we talking about? Scarce resource. These days, one very scarce resource for us can be water, especially in certain areas. You might find that rivers and streams are running dry and there is no water, or a very severe shortage of water. That makes water a scarce resource. In other words, this means it is not available to the extent required. The quantities are not enough to fulfill the requirement and the needs. So water is a scarce resource, especially in some areas. We have also seen in current times that for us electricity has become a scarce resource. Scarce because it is not enough to meet the full requirements of the people. That is, we are all experiencing power cuts, electricity shortage, resulting in what we call load shedding, power outages. So we are doing without electricity because there is not enough electricity being produced to meet the requirement. So that makes electricity a scarce resource. What else can be a scarce resource? We can also see very long queues and lines at CNG stations, vehicles waiting, because CNG or natural gas is not sufficient to meet the requirements. So that makes natural gas a scarce resource. People are having to wait a long time in order to fill the vehicles with CNG. Some areas even experience gas load shedding, so they do not get gas in their homes all the time. So that makes gas a scarce resource. So we are now talking about scarce resources where the resources are insufficient to meet the requirement. We can extend this in a way and say for us, one resource is the motorway. We have one motorway going from Lahore to Islamabad. That makes the motorway a scarce resource because it is not available in the rest of the country. So we have one resource, and so when we think of trying to maximize the usage, we have to try to maximize the usage from our scarce resources. There are other areas of shortages. You might think that our railway network is insufficient. So if that is a resource, it makes it a scarce resource. So we are trying to say that something which is insufficient to meet the needs of the people which are required, then that makes it a scarce resource. So in our case, we are going to confine ourselves to the manufacturing organization and look at the resources that they consume, the resources that they use. They use labor, they use machines, they use materials. So if these things are scarce, and in order to buy materials, they might use foreign currency. So at times, foreign currency is restricted. That makes it a scarce resource. So we are now going to find in the organization how to deal with the problems where there is a scarcity of resource and they have to then maximize the benefit from the use of these resources. Linear programming is a mathematical technique to give the optimal solution for the use of scarce resources. We referred to a simple example where if there was one scarce resource, then we find the contribution per unit of the one scarce resource, and we maximize that contribution by choosing the products that are going to give the maximum contribution per the scarce resource. Now, if there was more than one scarce resource, then it is possible that the contribution per unit of one scarce resource can be maximized in one product, but in another product, the contribution per unit of the other scarce resource is higher. So there would be then a complexity in situation in order to resolve that, which products to manufacture, to what extent, what is the optimal solution of producing products where there are different scarce resources and the contribution per the scarce resource can be higher in one case and higher for another product in another case. We'll see that by looking at an example later on. Application of linear programming. We established that where a scarce resource exists, the contribution per unit of the scarce resource should be calculated. The resource should then be allocated to different products on the basis of this contribution per unit. This will maximize profits. If we have more than one product and they are using a resource, let us say material, and the same material is used in both the products, if this material is a scarce resource, this means there is insufficient material to produce both the products in the required quantities. Then we said the procedure to adopt is to calculate the contribution per unit of this resource, the material. So the contribution per unit of material is calculated, and whichever product gives the higher contribution per unit of this scarce resource, that product is produced first. It is given priority and preference over the other. Where more than one scarce resource exists, the optimum production program cannot be easily established by the above process. Where material is scarce, and let's say also labor is scarce, and there are two products A and B. Now, if the contribution per unit of material is higher for product A, but the contribution per unit of labor is higher for product B, then this our procedure, our program is not going to provide easily the solution for which product to produce first and how much of the product to produce. And this is where linear programming is going to be applied. Linear programming is a mathematical technique. By use of mathematical equations and graphs, you can identify the point which is going to maximize profits for use under restrictive or scarce resources. Let us look at an example where even two scarce resources will be examined. The ZB company produces two products. The standards per unit of product are as follows. One product is the BB and another product is the MB. So two products, BB and MB. Selling prices are 110 and 118, less the variable standard costs. Materials. BB materials are 8 units at 4. So price of material is 4. 8 units are required. 32 is the cost per unit of materials in BB. Similarly, in MB, 4 units are required at the price of 4. The cost per unit of materials for MB is 16. Labor. The labor rate is 10 per hour. Now 10 per hour, BB requires 6 hours per unit. So the labor cost per unit is 60 for BB, and MB requires 8 hours per unit. So the labor cost is 80 per unit for MB. Variable overheads. It says in the notes at the bottom that variable overheads are based on machine hours. So we have the variable overhead rate of 1. 4 hours are allocated on variable overheads to BB, so the price is 4, and 6 hours are allocated to MB at the rate of 1, and that's variable overheads of 6. So total variable cost of BB is 96 and variable cost of MB is 102. The contribution per unit, BB 14, MB 16. We are given that during the next period, labor hours will be restricted to 2,880 hours. Marketing estimates maximum potential for BB sales is 420 units. So the example considers two products, the BB and the MB for the ZB company. The contribution from BB is 14 per unit, and the contribution from MB is 16 per unit. The BB requires 6 hours to produce, and the MB requires 8 hours to produce. we are given a scarce resource that the total amount of labor available in the next period is 2,880. So labor is the scarce resource. There is a restriction limited to 2,880. And we are also told that the maximum production of BB is 420. So the maximum amount of BB that can be produced is 420 in any case, but there is a labor total overall restriction on labor. Product BB yields a contribution of rupees 14 and uses 6 scarce labor hours. Hence, contribution is rupees 2.33 per labor hour. Similarly, contribution per labor hour of MB is rupees 2. So with a contribution of 14 per unit and each unit requiring 6 hours for BB, 14 divided by 6, you get 2.33 is the contribution per labor hour. Whereas for the MB, where 8 hours are required and contribution is 16, so total 16 divided by 8, this gives 2 rupees contribution per labor hour for the MB. Company should therefore allocate scarce labor hours to the manufacture of BB. Since BB sales are limited to 420 units, 2,520 labor hours will be used. This is 420 multiplied by 6. Seeing that the contribution per labor hour for BB is higher than that of MB, we should first produce BB to the extent of its maximum production. We are told that we can produce as much as 420 units of BB. So when we are going to produce 420 units of BB and consume 6 hours per unit, we are going to consume 2,520 hours. So this will be recommended that we should first produce BB with the higher contribution per labor hour and consume 2,520 labor hours in the production of BBs. The remaining 360 hours will be allocated to MB as 1 unit requires 8 hours, 45 units of MB will be produced. From the total of 2,880, if 2,520 are going to be used in the production of BB, we will be left with 360 hours for the production of the MB. Given that each MB is going to take 8 hours, we are going to produce 45 units of MB. So our total production will be 420 units of BB and 45 units of MB. This will be the normal procedure to follow in the scarce resource to maximize the contribution. Profits will be maximized when firm produces 420 BB and 45 MB. Total contribution will be rupees 6,600 as follows. 420 units of BB, contribution of 14 per unit gives a contribution of 5,880. And 45 units of MB at a contribution of 16 per unit gives contribution of 720. The total contribution is 6,600. So we are saying that the maximum contribution and therefore the maximum profit is going to be achieved by the production of 420 units of BB. Here the contribution per unit is 14, and that amounts to a total contribution from the BB product is 5,880. And we are then going to be able to produce 45 units of the MB. 45 units of MB where the production is going to result in a contribution of 16 per unit. So 16 per unit, 45 units is going to give a contribution of 720. So our total contribution is going to be 6,600, and this is the maximum contribution that can be obtained from the use of this scarce resource of labor. Limited resource labor 2,880. We said that we are going to maximize the contribution per unit, arrive at a total contribution of 6,600. Two resource constraints. Let us assume that both BB and MB use a common item of material, and supply of this material is restricted to 3,440 units in the next period. There are now two scarce resources, labor and material, and contribution per unit of scarce resource will be as follows. This example is now going to be extended. On the one hand, we had a scarce resource of labor of 2,880 hours, and we are now saying that both the BB and the MB, they both use the same material, and there is now going to be a restriction on the availability of material, and 3,440 units are going to be available in the next period. So now there are two scarce resources, labor as well as material. If we are going to calculate the contribution per unit for both the resources, let's see what happens. The contribution per unit for both BB and MB is given here. First, if we look at the contribution per labor hour, we saw that the total contribution per hour was 14. BB required 6 hours per unit. That gives BB 2.33 contribution per unit of labor hour. MB requires 8 hours, and the contribution per unit is 16. This gives MB a contribution of 2 per labor hour. So BB has a contribution of 2.33 as we calculated earlier per labor hour, and MB has a contribution of 2 per labor hour. Looking at the contribution per unit for materials, the contribution per unit of BB is 14, and we are told that it requires 8 units of material. So the per unit of material, the contribution is 1.75. And for MB, it requires 16 is the contribution per unit, and it requires 4 units of material. So 4 units of material required by MB gives a contribution of 4 per unit in case of MB. Here, the contribution per unit is much higher under MB than the contribution per unit of the BB. BB has higher contribution per labor hour, and MB has a higher contribution per unit of material. So when we look at the contribution per unit for the two products, the BB and the MB, we find that when we look at contribution per labor hour, BB has a higher contribution per labor hour, 2.33 against 2. And when we look at the contribution per unit of material, there MB has the higher contribution per unit of 4 compared to the 1.75 contribution per material for BB. So differing contributions per unit arise. One is higher for labor, the other product has higher for material. If both are restricted, then we can't use our earlier procedure of trying to maximize contribution and seeing which product gives the higher contribution per unit. So here we have to apply the linear programming technique, and we have to find mathematically what should be now the optimal solution, how much of BB to produce and how much of MB to produce. This is going to be solved by linear programming. Linear programming is a mathematical technique that can be applied to the problem of rationing limited resources among alternative uses in such a way that optimum benefits can be derived. It seeks to find a feasible combination of output that will maximize or minimize the objective function. So we are saying that the linear programming technique is going to provide a solution where there is a range of scarce resources. So the problem of rationing of the resources, how much to allocate to one product and how much to allocate to the other product, in such a way that the profit is maximized. So we have said that it seeks to find a feasible combination. So there is going to be a combination. We can produce so much of one product and so much of the other product. The combination that is going to give us the best result is going to be the optimal solution. So we need to find out, first of all, we need to establish what is the possible solution, feasible solution within the restrictions. Because there is limited resource, so we have to then work within a range, within a feasible area. First, we have to identify what is the area which is possible, what is the range which is possible to produce with the restrictions given. And secondly, we have talked about maximizing or minimizing an objective function. When we talk of maximizing, we are saying that the objective function or the objective is going to be either to maximize profits or contribution or to minimize the cost. So two objective functions can be made from various problems. So when you look at the scenario and when you find out what is the objective will either be to minimize the cost or to maximize the contribution and profit. So we have said that the objective function is what is going to be required, that we are going to find the feasible combination of output that will minimize or maximize the objective function. So objective, if it is contribution, then we will find out what combination is going to maximize this contribution and the objective of maximizing the contribution. The objective function usually takes the form of maximizing profits or minimizing costs. Usually there are going to be these two objectives. Either we try to maximize our profits or we try to minimize our costs. So within the entire restrictions and availability and the combinations, we first establish a range of feasible combinations of the two products that we are going to produce. So a feasible range, and then identify objective, either to minimize cost or to maximize profits. An objective function can be expressed also as an equation. In other words, in our example, the BB has contribution of 16, I think it has 14, and the MB has contribution of 16 per unit. So 14 of BB plus 16 of MB, a combination, these two together, we have to maximize. This becomes an objective function. Assumptions of linearity. Contribution per unit for each product, utilization of resources per unit are the same, whatever quantity of output is produced. This applies within the range being considered. Before we begin to apply the linear programming technique, let us examine some assumptions under which this technique is going to operate. So with all techniques and all other theories that we discuss, there are a number of assumptions that we have to keep in mind under which this technique is going to apply. Now, the linearity assumption is that it is going to be, the relationship is going to be a straight line relationship. In other words, that we are saying the contribution per unit of product will remain the same for the range of output. So we are not going to include any changes in the contribution per unit. Similarly, utilization of resource per unit. In other words, we said that one product is going to take so many hours of labor. Another product is going to take so many units of material. This utilization of resource will remain the same within our range of output. Whatever we want to produce throughout that range, the consumption of resource per unit and the contribution per unit is going to remain constant. It is going to remain the same. So this is one assumption. The other assumption is units produced and resources are divisible. We may see an optimal plan for production of 194.38 units, for example. This will be interpreted as 194 units. The next assumption is that the units are divisible. You can use any fraction of the resources available and any fraction of the materials or labor, etc. So this is going to then give us the solution in decimal terms also. We use the example of 194.38. This is just a hypothetical example to illustrate to you that the solution might end up in decimal points. If you get a solution in decimal points, whereas your production is only in whole units, then you can take the nearest whole number and interpret that solution as giving you the nearest whole number. So these are the two assumptions. First is that they are going to be constant. The contribution and resource utilization per unit is constant. And secondly, that the units are divisible and you can use small quantities of the units. The procedure to follow is, first, formulate the problem algebraically with Y denoting the number of units of product of VB and Z denoting the number of units of product MB. So now we'll look at the procedure to follow in formulating our linear program. For simplicity, we are now going to call the units of VB as Y and the units of MB as Z. So now we will refer to Y and Z in order to identify the two products. Secondly, we must specify the objective function, which in this example is to maximize contribution. The second step is that we are going to identify the objective function. In our example, the objective function is relating to contribution, and our objective is to maximize contribution. We will call contribution C. So the two products are Y and Z, and there are restrictions on material and labor, and we have to maximize contribution, which is C. This is followed by the input constraints. Constraints that we are going to consider are materials which are used in both products Y and Z, and there is a limit of 3,440, and labor hours, and there is a limit of 2,880, and also we know that the maximum Y we can produce is 420 units. These are the constraints. Objective is to maximize our contribution. The contribution is 14 multiplied by y, number of units of y, plus 16 multiplied by number of units of z. So 14 times y, 16 times z, those put together gives you the contribution, and this is what we have to maximize. We can now formulate the linear programming model as 1. The objective function, maximize c is equal to 14y plus 16z, subject to the following constraints. 1. 8y plus 4z is less than or equal to 3440. 6y plus 8z is less than or equal to 2880. This is the labor constraint. And we are also using another constraint, which is 4y plus 6z is less than or equal to 2760. This is the machine capacity constraint. We are adding this third constraint into our model. 0 is less than or equal to y, which is less than or equal to 420. This is the maximum sales. In this equation, we are saying that y is between 0 and 420. So y lies somewhere between 0 and 420, because 420 is the maximum. Of course, the minimum is 0. We are not going to have any negative production. And z is greater than or equal to 0. So z cannot be negative, but there is no limitation as to how much z we can produce. So z, there is no restriction, so z is simply greater than 0. This model now is showing us first the objective function. How is the objective function formulated? As I said, the contribution from y is 14, the contribution from z is 16. So whatever number of units of y we are going to produce, multiply that by 14, and whatever number of z we are going to produce, multiply that by 16. This gives the total contribution of z, that gives the total contribution of y. You put these two together, add them together, and you get the total contribution, which is c. So c is equal to 14y plus 16z. This is our objective function. Then we looked at the constraints. We have seen earlier the constraints of labor and material. For material, we were given that each y requires 8 units of material, and each z requires 4 units of material. So 8 multiplied by the units of y plus 4 multiplied by the units of z is going to be less than or equal to 3440. So 3440 is the limit, is the restriction on material. Similarly, y requires 6 hours of labor and z requires 8 hours of labor. So 6 multiplied by units, number of units of y that we are going to produce, plus 8 multiplied by the units of z that we are going to produce. This is going to be the total labor hours that we are going to use, and this must be less than or equal to 2880. So this is the next constraint. 6y plus 8z is less than or equal to 2880. We are adding another constraint of machine capacity and saying that 4 hours of machine is required by y and 6 hours are required by z. So 4y plus 6z is less than or equal to 2760. The other two constraints are, first, the y production maximum sales. Y is between 0 and 420, and z is simply a positive number. In other words, there is no restriction as to how much z we can make. This gives us the entire model, and this is the model that we are going to now use. These constraints can be drawn on a graph. So each of these functions can be drawn on a graph. And when we draw on a graph, all the lines that we just referred to. And these lines are going to indicate what is the feasible area maximum. That line, in other words, any point beyond that line is going to be outside the feasible area. It will cross the constraint. It will be more than the constraint. So we are going to draw the lines on the graph, identify what is our feasible area, and try to identify which is the point of maximum contribution. Graphical method. When no more than 2 products are manufactured, the graphical method can be used, but it becomes impractical where more than 2 products are involved. So graph is a 2-dimensional thing. One axis is a vertical, other axis is a horizontal. You can place 2 products on 2 axes. So when you are looking at 2 products, you can use the graph. But beyond 2 products, you cannot use the graphical method, and there the complexity goes higher into higher mathematics, and that situation is not what we are going to consider in our course, in this very course. We are going to consider a maximum of 2 products which we are going to allocate the resources to. Materials constraint. When y is equal to 0, z is equal to 860. When z is equal to 0, y is equal to 430. These 2 points on the graph, these 2 points can be identified on the graph, and they can be calculated by using our model, our function, the constraint from our function. Quickly go back to our slide, and it says the material constraint is 8y plus 4z is less than or equal to 3440. So this means that when we are going to put a value of 0 to y, then in our constraint, if y becomes 0, then z is going to be 860. Similarly, in our equation, if we make z equal to 0, then according to our constraint, y will be equal to 430. So using the constraint and choosing the point 0, so where y is 0, what will be z? That's the point that we can calculate. And where z is 0, what is the point? What is the value of y? These 2 points are identified on the graph, and they are joined together, and this gives you the line which is the constraint for materials. A straight line is plotted with y on the vertical axis and z on the horizontal axis. At z is equal to 0, y is equal to 430, up to y is equal to 0 and z is equal to 860. The area to the left of the line 8y plus 4z is less than or equal to 3440 contains all possible solutions for y and z regarding materials. So once this line is drawn, which is the 8y plus 4z is less than or equal to 3440, then anything above this line will not give you the solution of 8y plus 4z is less than or equal to 3440. So any area below the line is going to fall in our feasible area, as I said. The area, any point over there, any combination of y and z below that will fit into the equation, into the restriction. The labor constraint. The labor constraint 6y plus 8z less than or equal to 2880 indicates when production of z is 0, production of y will be 480. This is when production of z is 0, then 6y will be equal to 2880 and y will be 480. Similarly, if the output of y is 0, then z will be 360. We can now draw a second line at these 2 points, y 480, z 0 up to y 0 and z 360. area to the left of the line 6y plus 8z less than or equal to 2880 represents all possible solutions for the labor. So same as for the material, we can identify the points for our labor constraint. The labor constraint is 6y plus 8z is less than or equal to 2880. First, make y equal to 0, find out the value of z. Then make the value of z equal to 0, find out the value of y. Identify these 2 points on the graph, join them, draw a line, and that gives you the constraint. Any area below that is feasible, above that it is not feasible. The machine input constraint. This constraint is represented by z is 0, y is 690, and y is 0, z is 490. The line indicating the constraint is 4y plus 6z is less than or equal to 2760. Area to the left of this line represents all possible solutions for machine capacity. The final constraint is the sales output constraint, represented by the line y is less than or equal to 420. So exactly in the same way, we can draw a line for the machine constraint, machine capacity constraint. And that again is drawn by first assuming that y is 0, what is the value of z? And then when z is 0, what is the value of y? Join the 2 points together, and that gives you a line for this machine capacity constraint. The last constraint function we said is the sales of y. This is a maximum of 420. You draw the line of y is equal to 420. Anything below that can be less than or equal to 420. Anything above that, y will become more than 420, and that will not be in the feasible area. Let's examine what the graph would look like. So in this graph, we are showing all these lines that we have said. The constraint of sales y is equal to 420. The materials constraint of 8y plus 4z is less than or equal to 3440. And the labor constraint of 6y plus 8z less than or equal to 2880. So once all these lines have been drawn, we are going to look at the left side of all these lines. And so this little area where we have written C is equal to 2240, this becomes the feasible area. So this area, anywhere in between here, all constraints are being met, and any point that is selected here is going to give you a contribution that meets all the restrictions. So we have now the objective of trying to maximize the point, find the point at which in this area the contribution is going to be maximum. That is going to be solved by our linear programming. These are the constraints, and we will look at how we can arrive at a solution in our next lecture. That's all for this session. Thank you very much.